Today's talk is going to be given by Mohammad Farazmand, and his title is Extreme Events in Fluid Dynamics, Mechanisms, Prediction and Mitigation. Mohammad received his PhD in mathematics from ETH Zurich and studying under George Haller, who's also logged in just to check if everything's all right, in 2014. He then did postdocs at Georgia Tech with Predrag Cvitanovic and MIT with Themis Sapsis. Before in 2019, he became an assistant professor in the math department at North Carolina State. Mohammad's research interests span various topics in applied maths with an emphasis on reduced order modeling and data-driven analysis of dynamical systems. So it's a pleasure, Mohammad, to have you here today. Take it away, please.
All right, thank you very much for the introduction and for having me. So the talk, let me just get rid of the video and all right. So I decided to give an overview talk of the work I've been doing on extreme events in fluid dynamics and not go particularly deep into one, contribution. So this will be an overview talk. Here is the outline. I'll start with the general questions that, at least to me, are the important questions to address in the area of extreme events. And then I'll describe a variational framework that we've developed to get to the roots of what are the mechanisms that cause extreme events in general. And then I'll tell you that once you figure out the mechanisms, it allows you to do data-driven prediction of extreme events. And I'll show you 3 examples there. On first example, I'll spend some more time, but the next 2 examples, I'll go through them quickly and just showcase them. And finally, the mitigation of extreme events, I'll basically argue that once you know the mechanisms, it allows you to also come up with control strategies which would mitigate them. And finally, towards the end, if there's time left, I'd like to say some things about the prediction of extreme events from sparse measurements as well. All right, let me motivate this talk with this video. I apologize for the grainy quality of the video. But what you will see is when I play it, you'll see an aircraft going down the runway on an aircraft carrier somewhere in the middle of the ocean. And what I want you to pay attention to is that what happens when the aircraft gets to the end of the runway and tries to take off. So the aircraft goes down the runway, gets ready to take off, and a huge wave just before it takes off hits it. More interestingly, the pilot is so skillful that actually, if you see, the aircraft keeps flying and doesn't actually sink. This is not a jet airplane. If it was a jet airplane, in all likelihood, it would have sunk. So this is an example of kind of extreme events that take place in fluids, and you obviously see the point of being able to predict them before they take place. The case of mitigation here would be facilitated by the prediction, because if you could predict it, you would here just delay the takeoff by a few minutes and you would be safe. I have to mention also that there's anecdotal evidence from people on board the aircraft carrier that day that it was a very sunny, nice day. There were no storms. And nonetheless, this extreme wave came out of nowhere and hit the aircraft carrier. And this is the characteristics of the systems that I will discuss, that it's not that these extreme events take place necessarily because of huge disturbances from the outside, but it's just the nonlinearity of the systems that spontaneously create these extreme events. And that makes it rather hard to find out, especially in high dimensional systems, to find out what that mechanism is and what we can do about it. Of course, extreme events happen more broadly, not just waves. In turbulence, I'll show you an example. Actually, 2 examples where extreme events appear as extreme episodes of energy dissipation, extreme weather events. Outside fluid dynamics, there are extreme events that I will not get into it. Of course, these cause billions of dollars in damages. If you think of hurricanes, stock market crashes, things like that. Death, displacement of population, and erosion to the environment. And for all these reasons, it's really important to be able to predict them and, when possible, to mitigate them. Here's a diagram that I like that basically, to me, summarizes the different areas or aspects of extreme events that are of interest. At the middle, the core of it is the mechanisms that cause the extreme events, and the main part of my talk today will be about this part. But there's, of course, as I said, data-driven prediction, whether we can, from observations, predict these events before they take place, and control strategies to mitigate them. There's another area, which is the statistics, which doesn't try to predict individual occurrences of extreme events. However, it would say what is the probability of extreme events overall, probability distribution of extreme events taking place over a long period of time. So it's not capable of predicting individual extreme events, but gives you statistics over long run, how probable they are. I would like to emphasize that the mechanism is at the center, and it's really useful that you know the mechanism, because when you know it, as I will argue, it gives you indicator functions or precursors to extremes that give you warning signs of upcoming extreme events. It also informs the control strategy that you should take to mitigate them. It also helps to improve the statistical estimates of extreme events. But today I will not talk about this statistical quantification of extreme events at all. So I will focus only on these three aspects down here. So let me start with the mechanisms and say that my background is in dynamical systems, and there are some dynamical systems where extreme events take place and their mechanisms are known. For instance, there are slow-fast systems where these extreme events occur because of a fast time scale in the system and repulsion from a slow manifold. This is pretty well understood. There is rare transitions induced by some sort of noise when your system is driven by a potential, and those rare transitions are also, this mechanism is understood. It's basically the noise that kicks you towards a rare transition. There are heterokinetics cycles that cause extreme events. These are all very well understood. And if you're interested, there's a review paper we wrote a couple of years ago that goes through all these known mechanisms. However, these methods that I just described, they are very limited in their applicability because you have to have a very particular mathematical structure, for instance, for slow-fast systems, these methods to be applicable. As we know in turbulence, for instance, there is no such nice separation of length scales and time scales, and as a result, these methods are not immediately applicable. And the overall goal of this program is to push methods that are applicable to simple low-dimensional systems, here typified by a pendulum, towards more realistic systems that we really encounter in fluid dynamics. And this variational framework that I'm about to describe is an attempt at this. So the variational framework applies more generally to PDEs that are described by initial value and boundary value problems, Navier-Stokes being a typical example of them. So the system has this governing equations that I'm going to assume that is known and it's a model that we trust, as in Navier-Stokes. You provided some initial condition, you can numerically integrate it and create simulations. Once you're doing that, basically what you're calculating is the solution map that maps an initial condition u0 to a later time u at time t. U here is a function space or a state space of this dynamical system. I view these as dynamical systems, and U is that state space in which the solutions live in. Because I will talk about probabilistic predictions of extreme events, I also need some notion of probability too. So I'm going to assume that this system has an invariant measure that allows me to compute probabilities with some probability measure P. Now, so far I have said nothing about how I define extreme events. This is just a setup of the governing equations. Let me say something now about the extreme events. The way I define the extreme events is what practitioners do. There is some quantity, let's say some scalar function f that they're interested in. It maps any state to a scalar function. And if you look at the time series of this quantity, for instance, in the wave example that I showed in the video, that would be this maximum surface height, right? When surface height is large, you have extreme waves. So you look at this quantity as a time series, and in chaotic systems, it oscillates chaotically around some mean. But if you have extreme events, once in a while, there are these unpredictable bursts coming and going. They're short-lived, they're transient, and they seemingly come out of nowhere. There is no periodicity to their appearance. Again, a practitioner would put a threshold on this quantity and say, whenever I exceed this threshold, which is usually mean plus 1 or 2 standard deviations, if you exceed that threshold, you declare that an extreme event has taken place. People who look at the statistics of extreme events like to look at the probability density of this quantity as opposed to time series. And they also do the same thing. You put the threshold every time you're above that threshold, it's an extreme event has taken place. You can also do it the other way around if the extreme events correspond to small values of f, but you can do f to minus f, so that can be treated in the same way that I will just describe. So this is the intuitive way of looking at the extreme events. Again, here is the model. There are time series which have bursts that define extreme events. However, it turns out that it's not very useful to look at the time series of the quantity of interest and analyze that in order to predict extreme events. What I do instead is to look at the state space of the system, the function space in which the states are evolving. Now, the donut here that I've drawn is to indicate the attractor of the system. Of course, this is an illustrative picture, so the attractor could be a much more complicated set. But you have an attractor because the systems we deal with are often dissipative, so they have a lower dimensional attractor, although the function space itself can be infinite dimensional. And this is very important because anywhere else you start from, you always asymptotically or eventually converge to the attractor. Now your system is evolving on this attractor, and I envision the extreme events as follows. There are the small regions on the attractor that if you visit, an extreme event, which is typified by these excursions away from the attractor, will take place. So the idea is, why don't we look at these regions on the attractor, which are precursors to extreme events? And if we can identify those regions, probably looking at the properties of the states in those regions will teach us something about what causes the formation of extreme events. Here is the formulation of how to do this mathematically. So I have a quantity I'm interested in, f, which has these bursts in it. I have an initial condition that I don't know yet. Initial condition will end up being in these yellow regions, which are precursors to extreme events. I would like to identify that, but I search for them by maximizing the growth of the observable or interest over some time scale tau. So this time scale tau is a typical time scale over which the extreme events are developed. You can come up with some estimation of this tau from looking at time series of the quantity f. So once you have this estimation, you fix tau, and then you look for initial conditions u0 such that they maximize the growth of this quantity. Of course, you have to put constraints because you want your evolution of your states to satisfy the model, the initial value problem. And also, even more importantly, is that the initial condition, you want to enforce it to live on the attractor. In fact, it is easy, even for Navier-Stokes, to come up with initial conditions that over a very short period of time, they give you a large increase in the quantity f. However, these are, and you can write them down explicitly on paper. However, these are some exotic initial conditions that you never encounter in reality because they don't live on the attractor, they live somewhere else in the function space. So in experiments and observations, you will never encounter them. So you want to exclude those unrealistic initial conditions, and this second constraint that enforces the initial condition to live on the attractor does that for you. So this is an optimization problem, in other words, that is, as I said, is constrained, and the constraint, one part of it comes from the model that again, we assume we know, and the other part comes from the data, because even if you know the model doesn't mean you know where the attractor is. What we do, we use some data-driven method to approximate what the shape of the attractor is. For instance, POD or PCA analysis, when you do that, you're basically estimating your attractor with a hyperellipsoid, right? And that's the technique that, one of the techniques we use for data-driven approximation of the attractive. All right, this is this one slide that summarizes the method. If you're interested in the details, I would refer you to this paper up there. But let me show you an example of the application of this method. This is a two-dimensional Navier-Stokes equation known as Kolmogorov flow. What makes it Kolmogorov is that the forcing is very special. The forcing is just one Fourier mode. It's time independent. The Fourier mode is being excited at the mode Kf, which I put equal to 4. So wave number 4 is being excited. And nu is the inverse is a non-dimensionalized, so that's inverse of the Reynolds number. And if you look at the vorticity field, the Reynolds number 100, it looks something like this. Now, this is this, I call it the simplest Navier-Stokes possible because there is no stochastic forcing. There's no real boundary conditions. The boundary conditions are periodic in both directions. However, if you look at the energy dissipation, time series of the energy dissipation, rate of energy dissipation, you will see that it has this behavior that I described. It has chaotic oscillation, and once in a while, it has these large amounts of energy dissipation. So the question is, what causes this energy dissipation? And we applied our framework to this to find this mechanism. Again, I want to emphasize that it has nothing. It turns out that the appearance of these extreme events is not instigated by the external forcing. The external force is always present, is time independent, it's a constant, right? In time, it doesn't change, but these bursts come and go unpredictably. So it can't be that the external forcing is responsible for the formation of the extreme events. Here is the solution of the optimization problem without going into the details of it. And what I want to take away from this slide is the simplicity of the vorticity corresponding to the optimal solution. I also want to emphasize that these vorticity fields are not the vorticity field of a Navier-Stokes simulation. It's the vorticity field of the optimal solution of the variational problem that we have solved. If you look at the Fourier spectrum of it, you see that there are only 3 Fourier modes that are present. You see 6 spots here. Everything in white is 0 Fourier mode. Everything that is not white, basically you have some amplitude for Fourier, corresponding Fourier mode there. You see 6 spots because of the complex conjugation, but it's basically 3 modes present. The point I want to make is that it's interesting about this optimization approach or variational approach is that it removes all those unnecessary degrees of freedom that are not directly involved in the formation of extreme event. One could have said, if you're interested in the precursors to extreme events, why don't you run a simulation like this one and just pause it right before an extreme event takes place? But look at this movie. There are so many different scales involved in this, right? It's way more than 3 Fourier modes. If you pause it, there are a lot of other degrees of freedom that are involved in the simulation, but they don't contribute to the formation of the extreme event. But when you run the optimization problem and you get the optimal solution, it extracts those degrees of freedom that are active in formation of the extreme events. Now, all right, so we got these 3 modes out of this optimization problem. And the next thing, natural thing to do is that we looked at how they relate to each other. First of all, it turns out that these 3 modes do form a triad interaction. You know, the nonlinear term in Navier-Stokes comes in triads, where the triad interaction redistribute energy among themselves, and of course they interact with other triads. So it's a complex network of triad interactions, but nonetheless, the optimal solution has singled out this triad, which involves the forcing Fourier mode, a large scale Fourier mode 1, 0, and an intermediate Fourier mode, which is 1 kf to complete the triad. And we looked at the energy content in these Fourier modes as you run a simulation of Navier-Stokes. And here is the movie of these energy, or the modulus of the Fourier corresponding Fourier modes. And you see that something interesting happens. Once in a while, there is a distinct exchange of energy between these 2 modes. For instance, if you look at this one, the large Fourier mode, the large scales, or the smaller Fourier mode, lose energy. And at the same time, the smaller scales gain energy. And it keeps happening in this instant. And if you keep like looking at this again, this instant, it is happening. And it turns out that they almost coincide with the burst in the energy dissipation, the quantity that we were interested in. And actually, when you look at the energy dissipation in the Fourier space, it explains why this energy exchange between these two modes would lead to an increase in the energy dissipation itself. This is a large scale here, and it exchanged energy to a small scale. And we know that the exchange of energy to small scales means that if at least the total energy is more or less constant, it leads to an increase in the energy dissipation. So, all right, so far we have singled out the modes that are responsible for the formation of extreme events, and we've realized the mechanism by which these extreme events in the energy dissipation take place. It's the usual exchange of energy, but it's a very particular exchange of energy between particular modes that we have found. Now, the question is, can we use this observation, meaning that this exchange of energy, to predict the extreme events? And the answer is yes. And because luckily these exchanges happen slightly before an extreme event in the energy dissipation takes place. So the idea is, can we monitor, let's say, the modulus of A, and whenever it's small, it would signal that an upcoming extreme event is about to take place. So the answer is yes, but it's non-trivial to quantify that. And what we do is that we look at a conditional probability, where we have, here is the conditional probability, where on the horizontal axis, you have the values of the observable in the future. The future, or the prediction time here, is 1 time unit, which is roughly 2 eddy turnover times for this flow. The indicator is energy content of the lower Fourier mode. So remember that every time that becomes small, it signals an extreme event is about to take place. But we're looking at the minus that, so that whenever this is large, relatively large, it signals an upcoming extreme event. So the indicator large predicts an upcoming extreme event. Indicator small predicts no extreme events. And then there are 2 regions that you don't want to be in, which are the false positive and false negative predictions. Now, with the COVID tests going around and all this talk over the past year, we're all familiar with false positive and false negatives. It's the same scenario. False positives is when your indicator says that an extreme event is about to take place, but it actually doesn't. And false negative is vice versa. In short, you want your predictor to have minimal density in these 2 regions, right? And actually, this tells you that this indicator is a good indicator because it has very little density in these 2 regions. In fact, we were able to predict almost 96% of extreme events correctly, and any non-extremes we were able to predict almost 100%. Now, if I get more ambitious and start to increase the prediction time, I say I want to predict extreme events 10 time units in advance, then you start getting a lot of density in these two false positive, false negative regions. And it basically gives you a signal that what is your prediction time horizon by looking at these conditional probabilities. Once you have the conditional probability, you can also come up with a quantity which I call the probability of upcoming extreme events. And it's simply a marginal of this conditional probability. When it's small, this PEE, probability of extreme events, it basically tells you that there is no danger of upcoming extreme events. And when it's large, near 1, it predicts upcoming extreme events. So here is how this works in practice. This is a close-up view of one instance of extreme event. On the lower left, you see the energy dissipation, the quantity we're interested in. On the top right, you see the measured probability of upcoming extreme events and the vorticity field as on the right. So initially, you see that the probability of extreme events is 0 and the energy dissipation is relatively small. But you see that over time, the probability of extreme events shoots up, signaling an upcoming extreme event. And sure enough, shortly after, an extreme event does take place, which is this peak. I want to mention that in order to come up with a good indicator, we had to know the model. On the top of that, we had to solve an optimization problem. But once you do that and you discover what causes the extreme events, for prediction, you don't need to run a model anymore. If you are able to measure the value of the indicator, in this case, the modulus of a particular Fourier mode, then you can do real-time predictions with no simulations, no time integration, or anything like that. You don't even use the model anymore. So you use the model to discover the mechanism. Once it's discovered, it allows you to do data-driven prediction as long as you can measure the indicator that came out of the optimization problem. This was the first example that I spent rather a long time on. We applied this to two other systems that I will now very quickly showcase. One is a plane Poisson flow. You have two walls on the top and bottom, no slip boundary conditions. And it's a channel which is driven by pressure gradient. And in the other two directions, not in the z direction, in the vertical direction, the boundary conditions are periodic. Now, if you look at the energy, kinetic energy or energy dissipation, again, both exhibit these rather intermittent bursts. This system is one of those systems that had been studied a long time ago, and people had discovered what the mechanism is in this case. These are at least 3 papers that look at the mechanism of extreme events in this system. And it is known that there's a heteroclinic connection between two fixed point that causes this, or steady states that causes these bursts. However, we wanted to see if we can apply our method to this, and most importantly, if we can do early predictions of the formation of these extreme events. I will just show you a video of, again, a particular instance of a single extreme event. Pay attention to this graph over here, where it shows on the left, it shows the kinetic energy. On the right, it shows the probability of extreme events that I just described, the marginal of this conditional probability density, which, by the way, has very little density in the false positive, false negative regions. And see what happens. So you start with a probability which is relatively small, and then it shoots up near 1, indicating an upcoming extreme of the energy, kinetic energy, and of course, shortly after, an extreme of the kinetic energy happens. So this is, again, a close-up view of one instance, but we've done this for long-term simulations. And depending on how ambitious you are in terms of your prediction time, you can do 95 to 75% correct predictions of these events. 95% if you only predict 1 eddy turnover time in advance. And of course, the scale deteriorates as you go towards larger and larger prediction times. Like we went up to 10 eddy turnover times, and then it fell down, the prediction scale fell down to 75%. Another example is what they actually started with, which is the rogue waves or extreme waves in the ocean. The model here we use is a typical nonlinear Schrödinger equation that describes the evolution of slowly varying wave envelopes. U here is a complex valued function of time and space. Eta, which is the surface elevation, is given by taking the real part of this formula. And actually, the nonlinear Schrödinger equation, I'm sure most people here know, that comes out from a perturbation analysis of the water wave equation. So this is a perturbative, if you want, approximation of what happens to water waves. And the threshold people use in oceanography community for a rogue wave is that when the modulus of the envelope is larger than twice the standard deviation of the surrounding waves. Now, interesting thing about nonlinear Schrödinger is that it's a very rather nice system in the sense that people have discovered exact solutions to them. Here are 3 typical exact solutions that are known. More interesting for us, perhaps, is the Peregrine breather, which is localized in space and time. And here again is the wave amplitude in the vertical direction. It is mimics rogue waves because it starts from low amplitudes, goes to a large amplitude, and disappears. The other ones are a little weird because they're periodic either in space or time, but Peregrine solution has all the characteristics of the observed rogue waves that people have seen. However, I have to say that this is nice, mathematically very nice, but not very applicable in applications or in real situations, because ocean waves are 2D. This only applies to 1D waves. And also, there's something called the modified NLS, which is this perturbation solutions up to higher orders of accuracy. And as a result, it's a closer approximation to the real water waves. If you look at the modified NLS, it has several more terms here. And there are no exact solutions like this known to it. And in fact, I think there are no exact solutions known to it. It's a more complicated kind of PD. So all this nice mathematics doesn't apply there, but you still can apply our framework to that. And here is an example of what happens if you apply that. So here is a randomly generated synthetic wave field. And the wave group circled in red is the one that our method has identified as a dangerous wave group, which will develop into an extreme wave. And you see that as time progresses, it goes from small amplitudes to a large amplitude, and in fact passes the threshold of an extreme wave. Again, this is one example. We've done large scale quantification of the accuracy of the predictions, and it only has about 9% false positive or false negatives, and the rest are captured correctly. The prediction time in this case is 20 wave periods, which for deep water ocean waves is roughly 2.5 minutes. All right, let me see how I'm doing on time. All right, so this is so far all about the mechanisms that cause extreme events and their prediction. But what can we do about the mitigation part? So here is the control theory part of my talk. Let me start first by saying that going back, in fact, to the Kolmogorov flow, that two-dimensional Navier-Stokes flow that I started with. And in that case, now we've discovered what exactly causes the extreme event. The question is, can we disrupt that mechanism and as a result, disrupt the formation of extreme events? And the answer, luckily, is yes. The control term that we add, don't worry about this long equation. This is basically Navier-Stokes written in Fourier space. So U hats are the Fourier modes. And the term in red is the control term that we've added. What is important about it to note is that it only acts on a single Fourier mode. The Fourier mode that it acts on is the large scale Fourier mode 1, 0. The mode, to remind you, the mode that lost energy to a higher Fourier mode and caused the extreme events to form. So the question is, right before it loses energy, can we pump back energy into that Fourier mode and as a result, mitigate that transfer of energy between these Fourier modes? U hat is basically the Fourier modes corresponding to K naught. And then the most important part is that we have a time-dependent amplitude or gain for the control. And we put it to be equal to the probability of upcoming extreme events. So imagine that we're doing real-time predictions through our method of upcoming extreme events through this quantity, the probability of upcoming extreme events. So if we have no prediction, probability is 0, we have no control. We don't need the control. The amplitude is 0, the control is out. But as soon as there is a probability of upcoming extreme event, remember that the probability shoots near 1, and as a result, the control term becomes active. So in a sense, it's an adaptive control that turns on and turns off based on the prediction of upcoming extreme events. And here there's a video of, again, an individual extreme events and how this control acts. On the top left, you'll see the uncontrolled vorticity field. On the top right is the controlled vorticity field. And the bottom panel is the energy dissipation corresponding to the two simulations, one controlled, one uncontrolled. If you run that, initially, there was no prediction of upcoming extreme events. Control is off, and therefore the two simulations are exactly the same. One is Navier-Stokes uncontrolled in blue, and then one is controlled Navier-Stokes in red, but initially there is no control, they're off. But near the formation of an extreme event, we have a successful prediction that it will take place, the control kicks in and successfully mitigates the very large increase in the energy dissipation. We have done, of course, a long-term analysis of this, or ran it for a longer time. and gather the statistics about this. So if you look at the dissipation, probability density function of the dissipation for long-term simulations, you'll see that it has this heavy shoulder if you have no control. However, once you turn on the control, it has sort of a Gaussian looking probability density and no heavy shoulder. You can do that at larger Reynolds numbers as well, and you see the same thing. What I would like to emphasize here is that the individual trajectories, of course, change once you turn on the control at least once. Between the trajectories change between the uncontrolled system and the control system. This is a chaotic system. You kick it once, forever they're going to be on different trajectories. However, what is interesting is that we're not trying to make the turbulence to completely disappear and go to a steady state or a periodic orbit. The control system is still turbulent. We're not completely killing turbulence, but because it's so judiciously kicking in and killing the mechanism that causes extreme events at the right time and then disappears when you don't need it, the core of the attractor doesn't change and lets your system being chaotic. Let me maybe go back to the previous slide and run this, and I want you to pay attention to the vorticity fields of the two systems. You'll see that the vorticity fields, after even the control kicks in, they are of the similar nature. They're not very different. That's what I mean, that you stay on the attractor and you only kill off the part of the attractor that corresponds to the extreme events. All right, in the remaining time, let me just say one thing that is perhaps not related to fluid mechanics, but might be interest to some of the audience here. And it's the mitigation of rare transitions in stochastic differential equation or stochastic dynamical system. Consider a dynamical system where it is driven by the gradient of a potential and also excited by some noise. Here W is white noise, the Wiener process, so it is being excited by white noise. And we know that if we have no noise, of course, the local minima of the potential, which are here at 1 and -1, are asymptotically stable equilibria. You go there, you stay there. However, if you turn the noise on and you look at what happens to trajectories, it's also well known that once in a while you transition, the noise puts you over the potential wall here towards the other equilibrium and evolves around that equilibrium for a while, here being 1. And then if I show you longer time series, it will eventually come back near -1. And these transitions happen very rarely, statistically speaking. The question is, can we medicate this kind of transitions? Again, this is not directly related to fluids, but if somebody knows of these kind of bistable problems in fluid mechanics, I would be very interested to know too, because we have the control theory for it, and it could be useful to implement this on a fluid system. So the control system that we look at is a time delay feedback control. We add a control term U, which has this form. It's a constant, which is the control gain, alpha, times a linear function of the state, but there is a time delay in the state, and then XA, which is the desirable equilibrium that we would like to stabilize. So in this picture, XA is 1. We have a delay in there because any control system must have a delay, because you have to sense the system, send a control signal, actuate the controller. That introduces invariably a delay into the system. Now, a lot of times we just ignore it because it's a short time, and more importantly, it really simplifies analysis if you have no delay. If you have a delay, even if this is a finite dimensional system, as soon as you introduce a delay, it becomes an infinite dimensional system. Analysis becomes much harder to do. So usually people just ignore that, but we want it to be as realistic as possible. So we keep that delay in there. Now, an interesting thing that happens when you keep the delay in there is that the delay itself modifies the nature of the system, and in particular, it modifies the noise intensity, which here the noise intensity was sigma. But when you control the system, it essentially, I'm not going to go into details of this, but if you're interested, it's the details are in this first paper, but you can prove that the noise effectively changes, and the effective noise intensity becomes larger than the noise intensity in the uncontrolled system. as a result of that, you can't just use your control gain as large as you want. The larger the control gain in a non-stochastic system, the better the stabilization. But once you have a stochastic delayed feedback control, then you cannot just choose your control gain arbitrarily. And there is a sweet spot, therefore, for the choice of the delay and the gain that you have to choose. And in this paper, I discussed basically how coming up with an upper bound for the probability of transition, which is in terms of the delay and the gain, and it tells you how to choose the optimal gain and delay in order to mitigate this transition. Here is a one-dimensional example. This theory applies in any finite dimensions, but the one-dimensional example of this is here. The desirable equilibrium is at 1. There are these rare transitions if you have no control, but you turn on the control and you basically kill off all the transitions. And your system, probability density of the system from a bimodal distribution in the uncontrolled case, as a result, goes to a unimodal distribution for the controlled case. All right, that's all I want to say about the control. Maybe in the remaining time, let me say briefly something about prediction from sparse measurements. The problem here is that the well-known problem that we have continuum models that describe fluids on one hand, and on the other hand, we have sparse measurements of the state of the system. As a result, we can't just put the observational data into a solver and predict the system's future. And the question we're very interested to address is how can we do predictions of extreme events when we only are relying on sparse measurements? We haven't yet solved this problem, but I will show you a stepping stone towards that. Of course, this problem is not really new. It has been recognized for a long time, and data simulation is all about solving this issue. How do you integrate sparse observational data into a continuum model? And there are various ways people have proposed. However, these are generally speaking, especially variational data simulation methods are expensive to do, and as such, not ideal for real-time prediction. Another viewpoint that has been proposed, that I will follow this viewpoint, is that you do a lot of simulations offline. You create a library of data offline on a dense grid, as dense as you want. And then you have some simulations, and when you're you have some observations that are sparse, and when you want to do predictions, compare these sparse observations against the pre-computed library that you had created. And we'll go a little bit more details about that. Here are some of the authors that have contributed to this viewpoint. Here's a chart of how it really works, a simplified version of how it works. You have your numerical simulations offline. You've sampled your attractor, you've run long-term simulations, you store them offline. As such, you're really pushing the computational costs offline, and then if you're successful in this approach, it will allow you to do real-time predictions very quickly because you don't have to run real-time simulations. On the other hand, though, you have real-time sparse measurements from some sensors, and you feed these to the library and the measurements into some regression or machine learning method that tries to see how close your observations are to the states that are stored in the pre-computed library. And from this comparison, tries to do either reconstruct the whole flow field or make predictions about the future evolution of the system. However, invariably, to make that comparison, to compare the observed data to the pre-computed library, you have to invariably have a measure of distance or a metric that measures how close your observations are to the states in the pre-computed library of data. So we need a measure of similarity. Even if you didn't have observed, sparse observations, you had a very dense grid and you were given fields, for instance, vorticity fields of a turbulent flow. It's not trivial to measure, this similarity between two fields. If I gave you the field on the left and I asked you which one of these two fields on the right are closer to it, it's not, to the naked eye, it's not obvious. you may want to look at the L2 norm between these vorticity fields and say whichever has the less L2 norm is closest. But there's no real reason that L2 norm would be a good choice. In fact, maybe you want a low pass norm like H-1 norm, or a high pass filter like H1 norm. And those might be better because they select scales that might be relevant to your problem. Or more generally, so maybe there's some other metric that is much better. So one of the questions that we want to address in this is, what is the metric? The focus of our work is, what is the metric to use in order to measure the similarity between observations and data. Of course, this problem of the metric is well known in computer science. The famous example of it is the Swiss roll, where for clustering, you don't want to look at the Euclidean distance between each 2 points, but the length of the curve that is connecting the 2 points and lies on the surface, because this data has a lot of structure. It lives on the surface. This is well known. However, in our case, each point now is a field like this. And moreover, we don't have all these points measured everywhere in our field, but we have sparse measurements. So the goal is to address these two issues. As I said, we haven't solved the problem for extreme events, but we have made some contribution towards the case where you have systems which are multi-stable. Again, you have a PDE where it has coexisting asymptotic stable attractors. These attractors could be periodic orbits, steady states, quasi-periodic orbits, or even chaotic attractors, and they could be coexisting. And based on the initial condition of the system, you will either go to the periodic orbit or to the steady states or the other kinds of attractors. These dots here are symbolizing the labeled initial condition in your pre-computed library. This is your pre-computed library. You know everything about them. You've simulated them, and then you label them according to which attractor they converge to. And then someone gives you a new data point. There are two things to note. Each point, again, here is a field, and this new data point has an underlying field, but you have only sparse measurements of it. So the question is, how do you decide which cluster this point belongs to? It becomes more complicated if I, remove these lines. It's not obvious which attractor this the empty circle will converge to. Here is a more concrete example. It's an Advection-diffusion equation. I won't go into details of it. Let me just say that it has 4 attractors, which are all of them are steady states. 2 of them are constant at 1 or 0, and the other 2 have a tangent hyperbolic looking profile. The question is, somebody gives you an initial condition, which of these 4 do they converge to? Let me maybe just say about this problem. I realize that I'm running out of time, so maybe speed up and just say that we focus on a special class of norms, which are these weighted L2 norms. Phi here is the weight that we would like to learn. And the way we learn it is as follows. First of all, we have these labeled data, each of which is a state from the pre-computed library. And we would like to, we split them into 2 pairs, 2 sets. One is pair of data that converge to the same attractor. The other set are the pairs of data that converge to different attractors. So these are the dissimilar set and the similar set. And then we solve an optimization problem whose solution is this unknown density phi. It has a, basically the way it works is, in short, is that it minimizes the distance between similar points and maximizes the distance between dissimilar points. But what we have done also is that to introduce a sparsity promoting penalization here, which turns out to be very important because we want to be able to quantify this norm from sparse measurements. And this L1 norm does that for you. But it turns out that if you just have this L1 minimization, the solutions to the optimization problem without this L2 will be degenerate. But if you add an L2 norm, it regularizes it and gives solutions that are not degenerate. Let me just skip, maybe for the interest of time, over these 2 slides. These are basically the optimal solutions for the density as lambda, the sparsity parameter increases. The main point is that the sparsity parameter, as it increases, it goes to two distinguished points. These green curves are basically the density being concentrated at 2 points, which is around plus minus 0.7. Basically, the learned density is telling you that these are the points where you have to make measurements. In other words, it informs where you should put your sensors in order to do best possible predictions of the attractor at the end. Let me skip through that. So when you apply this, if you put your sensors at these optimal points where the optimization problem tells you, you have relatively low classification errors, which is around 5%. If you increase the number of labeled data, meaning the size of the offline library that you have created, you increase that, you get better and better predictions, and it finally plateaus around 5. But if you use two different points, which are not optimal, they're not put at around points plus minus 0.7, you get significantly larger classification errors. So the metric learning algorithm has worked as it should and had found the optimal sensor locations. Maybe let me just put the summary up here for you to read and stop here and see if there are any questions.
Oh, that's great. Thank you, Mohammad. Okay, all right. So the variational problem, yeah, there. So for the Kolmogorov flow, how did you somehow define the special set A for the initial condition search?
This part. So
Yeah.
we constrained ourselves, let me see, to a constant energy dissipation hypersurface in the function space.
Ah,
Yeah.
okay, nice.
Yeah.
Follow-up question.
I should mention though, for the three-dimensional channel flow,
yeah,
we did PCA basically.
PCA, right? Okay. And did you get any problems getting your algorithm to converge because your trajectories are chaotic, right?
Yeah. No, it was actually pretty straightforward. The usual the gradient descent converged.
Really?
Yeah. I mean, of course, there were cases where it converged to a local minima, which we discarded. Yeah. If that's your question.
Well, it's just you got. I guess Tor was quite small, was it? In terms of the exponential separation of initial conditions. That's
very small. In fact, we did two versions. One which is the instantaneous version of this optimization problem, where you sent out to 0.
Right.
And look at the instantaneous rate of increase.
Right. Nice.
And
right.
then a small tau but the results were very similar. The optimizers, interestingly, for the again the three-dimensional flow was more challenging because this instantaneous rate gave us garbage. For that case, we had to do the finite time optimization.
Okay.
Hi, Mohammad. That was a really nice talk.
Thank you.
I'm interested in using the methods anyway, and I would have a question about the prediction. If you can go to slide 15.
All right.
To me, it seems like you can predict the event just before it's about to happen. I mean, it's when your probability goes up, the event is already starting. Is this an intrinsic feature of the flow, or it can be improved?
So you see that, okay, let me maybe pause here. That's a good question. So here it goes up, let's say, right? But this value is kind of comparable to this one, right? So this has gone up too, but no extreme event took place. So if you just look at the time series and say whenever it's going up, and then we declare an extreme event, then you get.
I think that the quality of the prediction, I think, is really great. I mean, you have shown this. My question is more like, it seems that you can predict the event just before it's about to happen, or maybe it's a time scale. I'm thinking about the.
That's what the point I was trying to make about the prediction time horizon, right? Of course, these are chaotic systems, so I can't do arbitrary long systems, right? But and you can be more forgiving and increase the prediction time horizon.
Okay.
You tend to eddy turnover time, but you keep getting more and more false positives, false negatives as you do that. Get more ambitious and want to do long-term predictions, right?
Okay, so that's because of the Lyapunov exponent, so to speak, the dominant one, which sets this sort of work.
Exactly, yeah.
Okay, thank you.
Yes, hi, thanks for a very intriguing talk. My question is the only source of these extreme events the exchange of energy from lower to higher Fourier modes, or is there any other source from the Navier-Stokes?
Oh, could be other sources. The problem we looked at in this case, this turned out to be the mechanism. We didn't prejudge what it should be, right? It just came out of the optimization problem that there is this energy transfer for the Kolmogorov flow that causes it. You have different boundary conditions, different forcing mechanism. It could be very different, but you can still apply this variational approach to it and figure out what it is. All right.
How does the optimization procedure scale with dimension, e.g. 3D fluids problems or 6D kinetic problems?
Not favorably.
I was afraid that was going to be the answer.
Of course, it becomes very hard. In fact, in the case of the 3D, you had to, in some sense, cut some corners, if you will, and by reducing our search to the, I think it was 10 first PCA modes. So we reduce, compute PCA modes, and then it becomes a 10-dimensional. If you put the cutoff at 10, it becomes those 10-dimensional optimization, basically. Right. But I suspect as you go to more challenging geometries, higher Reynolds numbers, then that 10 becomes 100 or 1,000, more becomes more and more challenging in higher dimensions, no doubt.
Okay, here's a follow-up question. Is your work known in the fusion plasma community? I think they have plenty of problems to do with rare events and mitigation.
I'd be offended if it's not.
Well,
I'm kidding. But,
good answer. Okay.
No, I'm kidding. I hope it is. I mean, been giving talks about this, and if it's not, I hope somebody brings it up to their attention. I agree that it would have applications there. On
slide 13, you said that once the model is known, one can make purely data-driven predictions. But surely that is only true with the same mode pairs that the model had once identified remain coupled for infinite time.
Well, I mean, in Navier-Stokes, they do, in this problem, they do remain coupled for all times, and their energy transfer every single time. Again, if I go to maybe the prediction scale, it's 96% of the time, this has been successful, right? So it means that almost nearly every time an extreme event took place, this energy transfer was responsible for it.
Question 1, is the time of prediction included in the optimization problem? If so, do the optimized structures change with the time distance?
That's a very good question. So this prediction time T sub P is not included in the optimization problem. The way you pick it is that, again, you vary it and try to be as ambitious as possible. But as you increase it, you get more and more false positive, false negatives. Again, you're dealing with a chaotic system. It's inevitable. Always you get, at some point you will get, you will lose prediction skill. So that's how you basically pick this time horizon, which is how much false positive, false negatives you can live with, right? In this case, they were very low, and you can increase them, I think, to 6 eddy turnover times, but like around 10 eddy turnover times, it becomes a random prediction, 50% by that point. Right. Other time scale, probably that the question might be referring to is this tau. Yeah. This time scale over which the extreme events, form. This we do not vary, but in fact, you can include it in the optimization problem. We fix it from time series analysis, but you can, make that also a search you make. In other words, you can solve a minimax problem where you maximize the growth over a fixed period of time, and the minimization is over tau. So the minimum amount of time it takes to reach maximum growth.
Right. In the case of channel flow, The temporal distance between the peak in the indicator and the dissipation seemed to be very large, about 100 eddy turnover times. But the predictions are on the order of 1 to 10 eddy turnover times. How is the error measured?
How is the error measured? Well, the predictions are a binary prediction, right? Whether an extreme event will take place or not. So the error is basically whether you predicted correctly or not, divided by all the predictions you have made. More accurately put, the prediction scale is the sum of the densities in these two regions, and the error is basically the sum of the densities in the false positive, false negative region, and another way to put that.
Okay, great. So now a question from Mohammad. Can we replicate the control term to prevent extreme events such as stall in aircraft?
That's something I've been talking with colleagues with, something we're working on.
That's a bit of a scale up from what you were doing, but I think it's a good target.
Yeah.
Can the framework also be used to predict the magnitude of an extreme event?
That's a very good question. In the case of rogue waves, we kind of did that. And the details of it, I would refer you to the paper to see that. In fact, the predictions are so good that it's kind of almost on a, if you look at the predictions versus the real value of the rogue waves, it's almost on the x equal y-axis. Pretty good. But it's very particular in that case to rogue waves because we know so much about the NLS and modified NLS that we were able to do it. But more generally, at this point, it wouldn't. Is not integrated into the variational problem, but it's a good point to address.
May I jump in with another question on rogue waves? I am Francesco Fedele from Georgia Tech. Hello, Mo. How are you?
Good to see you.
I have a question. So a very interesting talk and very good work. I want to ask, you did the 2D dicey equation. So basically, you model ocean waves in a two-dimensional field. So basically, energy can spread directionally, and all the modulation instability and heteroclinic connections that you're gonna have in the NLS, you don't have it there. So usually rogue waves in 2D fields are mostly due to linear dispersion. It's classical linear focusing. Waves coming from different directions, and they all meet almost in phase. So I'm curious to know your optimal solver. So what did your optimal solver spit you out? What is the structure that you got from the optimal solver, and what was the indicator that you use to do basically the prediction of rogue waves? And then I will also I noticed there are spurious oscillations in your simulations of the dicey equation. Maybe that's maybe you use a very low time marching scheme. So that's I noticed very but that is is not relevant. So this is second. But I'm more interested in the what is the physics? What is the physical mechanism? Like in Kolmogorov, you found out that there is the triad interaction. Okay. So now for the 2D dicey equation, which mechanism did you find out?
I got your question. Yeah, good question. I don't know what you're talking about, the spurious oscillations. I don't think there, but the for mechanism for formation, again, we don't prejudge what it is, whether there is modulation instability or not in 2D. We don't do it. However, I would say that our viewpoint is that it's not just the nonlinear superposition of random waves. It is wave groups with particular length scales and amplitudes that the nonlinearities would evolve them into a rogue wave. And the question was, what are those combinations of length scales and amplitudes? And you're very right about the directionality. In fact, we did several spreading angles for the simulation, and how how many extreme waves you get does depend on the spreading angle significantly. But we did a full study in the paper with the spreading angle and all that.
And so the optimal solution, how did it look like? Was a wave group?
Yeah.
So then
we assume, actually, we assume or constrain ourselves to the class of Gaussian wave groups, but we don't fix the length scales or amplitudes. We search for those.
Oh, okay.
Yeah.
Okay, thank you.